partner. All right, it's 11:30. We are live, awake, and alert, and enthusiastic. And so hopefully this won't bother you guys too much. But I'm after we talked last class, I was spending way too much. We were spending too much confusion about running time, the running time period versus encoding. So and remember, we had compile time and we had run time. So in the slides, I changed it to coding phase and execution phase. So what does that look like? Here we have a history of events. We have when the problem is defined, and then the algorithm is defined, and then the input is defined, and then we check to see whether the algorithm solves the input on the given input, right? So here I talked about coding phase is the period of time in which you're coding up the algorithm, and it doesn't depend on the input. And here I made reference to compile time errors. So versus the execution phase is after the input comes, you execute the program and until you find out whether it has the right answer. And here's just the word we used before. This is when runtime's errors happen. This is when compile time errors happen. What do you think? Is that better? Anyway, that's what you got there. Let's move forward to B. So here, this one, we started talking about just sort of casually, but we didn't really cover it. So let's do this example, right? These are things like this is what I want people to understand. The reason I'm teaching this course is so that people can look at a sentence like this and know what it means. All right? And so let's use this woman's method of going in the inner to outer and looking at, see here, here's the inner statement. So because it has no quantifiers, the algorithm, the input, and the number of lines of code are all free variables. They have no quantifiers. That's why it's in a green circle. And we can say, what does it say? And it says input I, algorithm A has K lines of code. That's what this says, right? And then we bring in the next quantifier, and now the free variables are just algorithm and the K. We don't really need to talk about the input anymore. So we only talk about the input sort of as a side issue. Here we say algorithm A has K lines of code. And what is it saying? It's saying, well, that's independent of the input, right? For all inputs, the algorithm has the same number of lines of code, right? So that is saying independent of the input. And remember, that's people kept asking, well, why did I put the input in here, right? So that you could see that this sentence here says that it's independent of the input. All right, so now we bring in the next quantifier. Algorithm is quantified with saying there exists an algorithm with this property. And so what we're saying is, yeah, there is an algorithm. So I guess here I am just reading it like, there is an algorithm with K lines of code, right? Independent of the input. And then we want to say every K has this property, right? So we're saying for every K, you give me some K, and I can give you an algorithm that has K lines of code, right? There are algorithms with this number of lines, with any lines of code. And then it will be independent of the input. All right, I don't know if that helps, but let's then play the game. All right, what is our game? The game is the adversary. It's a for all k at the beginning. So the adversary gets to choose the number of lines of k that are allowed. And that's kind of funny. Why is the adversary choosing the number of lines of code, right? But the reason the adversary is given the k is because our whole goal of the sentence is to say that, well, what we're going to say is true for any number of lines of code, right? Given the number of k, we can build an algorithm that has so many lines of code, right? The adversary is invested in proving that the sentence is false, and hence the adversary is going to come up with some k that's particularly hard, right? And then given the k, once we know k, then the prover, it exists, right? So the prover then comes up with an algorithm, right? And he has a constraint. What are his constraints when he comes up with this algorithm? The constraint is that it must have exactly k lines of code. Now, the good news is that there's no problem. There's no P, right? There's no mention of a computational problem. So there's no restrictions on what this computational problem does, right? And then once he comes up with the algorithm, the adversary comes up with an input, and the algorithm's what's the adversary's goal is to make this false. So if there's some input in which the number of lines of code changes, then he will come up with that input. But all inputs are the same. All right. So now I'm claiming we have to know, is this sentence true or false? And I'm claiming it's true. And because it's true, we have to come up with a strategy in which the prover can win. So here it says for all k, so we say let k be an arbitrary value. Now, I'm here making it more of it's a joke where the adversary is nervous because he's going to lose, and so he's giving a really big value. But in the proof, we would be saying let k be arbitrary, right? And then knowing the k, here we have k is 1,000,000. Knowing k, the adversary has to write code, and he writes k lines of garbage code. Doesn't matter what they do. He just writes in k lines of code, and he calls it A. Then the adversary comes up with some input, and we say the adversary doesn't want to play because he's going to lose. So we let I be some arbitrary input, and then we say, oh, look at the algorithm does in fact have k lines of code, right? So the adversary wins, right? And what are we saying? We're saying it's true. The algorithm designer can build an algorithm with any number of lines of code, and that number of lines of code will be fixed, right? Does that make sense? People get this example? Good. All right, let's switch it up a bit. Now we're bringing in a computational problem, right? So we do as we did before. What are our free everything's a free variable. So what is it saying? We're saying on input I, algorithm A, it does two things now. Algorithm A solves the problem, and it has k lines of code, right? So in order for the prover to win, there's two requirements now. All right. So
I'm sorry, I had a question.
Yep.
In terms of what you're saying, because we start with for all of k, would we say that A, the algorithm, and the input are both functions of k?
Yeah, certainly you're not on this slide, you're on it later on, but certainly adversary gives me a k, I give you an algorithm.
Okay.
So it is a function.
But not I? I is not a function?
Well, yeah, I is a function. When the adversary chooses the I, it's a function kind of both of k and of A, yeah.
Oh, okay, makes sense. Thank you.
It sort of depends on who's trying to win. if the prover's trying to win, then yeah, either way, the guy here, I, knows A and knows K. All right, let's go back to the slide here, right? We're saying algorithm A computes problem P with K lines of code. Here you notice we didn't mention the input.
Sorry,
and then when we say there exists an algorithm with this problem, with this property, right? There exists an algorithm that can solve P with K lines of code. Then we're just saying problem P can be solved, right? Here we're just talking about P and K. What do we want to say about P and K? Problem P can be solved with K lines of code, right?
Sorry, I have a question about the K.
What?
I have a question about the lines of code. Like,
yeah.
If your algorithm doesn't depend on how many lines of code you have, then
the algorithm does. Oh, no, the algorithm definitely depends on the number of lines of code, right? I give you a piece of code, you can count how many lines it has.
Oh, it's the input that doesn't depend. Okay.
Yeah. The number of lines of code doesn't depend on the input.
Oh, okay.
Right? All right, so this is saying, right, we're saying something about P, right? What is it saying about P? P can be computed with any number of lines of code, right? All right, so now let's play what's the game? Well, Simak asked, is it a function? And here's how it's a function. The adversary gives me an arbitrary K, and given that arbitrary K, the adversary gives me a K, then the prover has to come up with an algorithm. And yes, that algorithm will be a function of K. You give me a different K, I will give you a different algorithm, right? Why? Because my algorithm needs K lines of code, right? And but now look at, he has come up with this algorithm, and as before, he's constrained that it has K lines of code. But the bad news is that now it must also solve computational problem P. And he knows this is going to be hard, right? He's a little worried about it. All right, so after he comes up with the K, after he comes up with the algorithm, right? So now we know the K, now we know the algorithm. The adversary chooses an input, and we see who wins. We win. The prover wins if both A has K lines of code and on this input it solves the problem. All right, so is this sentence true or false? I'm claiming this sentence is false, right? It's false. And let's prove that it's false. Well, to prove it's false, we need a strategy for the adversary, right? So we're going to tell you what the adversary does, right? The adversary is very happy because he knows he's going to win. The adversary knows maybe the computational problem P is a perfectly good computable problem. Maybe it's sorting, right? Maybe it's squaring. It's a good problem that's computable. He knows it's computable. And in fact, he knows many algorithms that can compute it, right? If P is sorting, he knows that quicksort can sort it, and merge sort can sort it, right? It can solve it, right? But P is not so easy. You know, it's not completely easy to write a sorting algorithm. There's some minimal number of lines of code that it takes, right? So he knows that P you can't sort with too few lines, but he's not going to spend too much time figuring out what the exact minimum is, right? Instead, he just says, hey, let K be 2, right? He knows 2 is a hard number of lines, right? He could even say maybe K is 0, but that would be rude, or K is 1. So he's going to say K is 2, right? So his strategy, he sets K to be 2. Now, what does the adversary do? The adversary, here we're going to say let A be an arbitrary algorithm, because that's what, but we're going to let the prover have a chat anyway. The prover no longer wants to play because it doesn't seem like a fun game, right? But he can easily come up with a program that's 2 lines long. and he can easily come up with a program that solves P, right? But he can't do both at the same time, right? So instead, right, he comes up with some algorithm, let it be an arbitrary algorithm, and he hopes for the best. All right, so now it's the adversary's turn again, right? The adversary said K is 2. The algorithm came up with some sort of arbitrary algorithm, and now it's the adversary's time to come up with an input, right? And he knows that at least one of these things is wrong, right? So the adversary is going to win, right? So I guess I guess I should have added more lines here, because this isn't really a good proof. So instead, I'm going to add some more here. I'm going to say, well, the algorithm is going to study the code, and if the algorithm doesn't have 2 lines of code, it doesn't matter what his input is, and this will be false. And if the algorithm does have 2 lines of code, then the algorithm will study, well, maybe there's some inputs on which it gives the right answer anyway, but there's some input in which it gives the wrong answer. So he'll come up with an input in which it gives the wrong answer. So I should remember to change those slides. That's not very good. So what it says it's false. There's some minimum number of lines that the algorithm needs below which it can't solve the algorithm. Right? Does that make sense? Are people following this?
A quick question. The example previous to that one we just did was we didn't have the
problem.
Algorithm at input equals the algorithm. Okay, all right.
Right. Then it's easy. He just needs to come up with an algorithm with 2 lines of code or the million lines of code. That's easy. But coming up with an algorithm of 2 lines of code that solves the problem, that's hard. All right, so here we're going to do another one, right? And I don't have a sense whether all of you guys out there are finding this too easy or too hard. I don't know. I certainly know that this was on a test, and almost everybody got it wrong. So that's why I'm going over this. So here we want to know, what does this mean, right? Can you read this and know what this means? Well, let's work on the inside out. Here we have everything's a free variable. What is this? This is saying what we've said before. On input I, algorithm A has K lines of code. We bring in, same as what we did before. Algorithm A has K lines of code independent of the input. Right now, now we're saying there exists a K. All right. So here, what are we saying about algorithm A? Well, it has some fixed number of lines of code. That's what we're saying. And this number doesn't depend on the input, right? We're saying there exists a K for which algorithm A has K lines of code. So we're saying algorithm A has some fixed number of lines of code, right? And that's true about every algorithm, right? Each algorithm has some fixed number of lines of code, right? So this is saying something different we said before. Right now, before we were talking about there were algorithms that had some number of lines of code, but maybe there were algorithms that didn't have a number of lines of code, right? We were just saying some of them did, and now we're saying every algorithm has a fixed number of lines of code, right? It's not just that there were some algorithms that have fixed number of lines of code. Now we're saying every algorithm has a fixed number of lines of code. So the game. The adversary, it's sort of strange, but the adversary is the one who gives me the algorithm, gives me the code. And then, right, why do we give this power to the adversary? Well, because the whole point of the sentence is to say something about every algorithm having some property. So the adversary will give us, invested in making that this is true, so the adversary will give us some algorithm that's very hard, right? And then knowing the algorithm, the prover's job, again, we're not talking about a computational problem, right? The prover's job is just to study this algorithm, determine how many lines of code it has, and give that K, right? And then, well, then we want to make sure that that algorithm has that number of lines of code for every input. So if there's some input in which the algorithm doesn't have that number of lines of code, that's where the adversary chooses it, right? And then we check, does the algorithm have k lines of code on this input? And that's the game. So hopefully you all know that this sentence is true. Why is it true? We're going to give an algorithm for the prover, right? Right? So when we say a prover goes first, the adversary goes first and gives us some algorithm, right? The adversary thinks it's a dumb game, right? Because he's going to lose. The adversary chooses an algorithm where it's not really clear how many lines of code it has, right? Maybe is the line of code beginning here or is it ending here? It's not clear. Maybe there are a lot of lines that have just brackets on them. Do we count those? Do we count a line that just has brackets on it, or do we not count a line with brackets on it, right? So anyway, the adversary gives us an arbitrary algorithm that could be really hard and confusing, right? And now the prover's job is to count the number of lines of code, right? And determine how many lines it has. Then once we have an algorithm, the adversary tries to confuse things by giving us some complicated arbitrary input, but that doesn't help any because the algorithm does in fact have this number of lines of code and we win. Are people following this? Right? This says each algorithm has a fixed number of lines of code that doesn't change with the input, right? Versus this guy over here, everything before talked about the existence of an algorithm. So it's possible that there were some algorithms out there whose number of lines of code depended on the input, and we weren't talking about them. But this one's saying, no, that's not the case. This is something that's true about every algorithm. All right? So now let's do this one. This one we've seen many times before, right? And you've already seen the picture down there. The picture was of our Clockwork Orange guy, so you should recognize this. Right? Is this true? For every input, there exists an algorithm, right? Remember the function. This is a function. You give me an input, I give you an algorithm. That seems kind of silly, right? So what does this say? This says algorithm A solves problem P on an input I. Actually, some earlier slides, I changed the slide as well to emphasize that this doesn't really imply that, let's go back to this. This doesn't necessarily say algorithm A solves the problem. What it says is algorithm A happens to give the right answer on input I, right? So then we're saying, what's true about this input in this problem, right? What's true about the input in the problem is that for this input I, problem P can be solved, right? I don't know about the other inputs, but for this particular input, the problem can be solved, right? And now it says for each input, the problem can be solved. But note, the algorithm can depend on the input, right? And this is our Clockwork Orange kind of thing, right? For every input, there can be a different algorithm, and we don't like that, all right? So here, now we switched it around. Now we're saying for every input, there exists an algorithm, right? And this is our classic way we solve things, right? Here we're saying for every here we're playing the game again, but sorry, we're still on the same one, right? So the input, here the adversary gets to come up with the input first. It's unusual. The adversary chooses an input, and right, he comes up with some input that feels like it's particularly hard for this problem, and right, so he chooses some input that's hard for the right. He doesn't have the algorithm, so it's not like it's hard for the algorithm. Somehow it's hard for the problem, right? And so then knowing the input, the prover designs the algorithm and he knows the inputs I in advance. So he only needs to make the algorithm true to work for this particular input, right? It's like knowing the exam question before you study, right? You don't have to study everything. You don't have to make it work for all inputs, all questions. You just have to get your algorithm to work for this particular input, right? All right, so that's the game, and right. So solving problem here. The point is that solving problem on any particular input might be hard, but and the adversary gave us a hard input, right? So this is again where I'm saying, well, can we solve this problem on this particular input? And that's where we're kind of restating the problem here, right? The algorithm A doesn't actually need to solve computational P. We're given the input. So the algorithm's not needing to solve the entire problem. He only needs to produce an algorithm that gives the correct answer on this input, right? So here, let's try to prove that this sentence is true, right? So the adversary gives us a really hard input. Let I be an arbitrary input. Then I come up with an algorithm that, right? I work all, the adversary works all day and night and figures out that the computational P on the hard input has answer 5, right? So what code does he give? He gives an algorithm that simply outputs 5. And so then this is true. And so the prover wins. Does that make sense? Right? He comes up with an algorithm that outputs 5. 5 is the right answer for this input. So this is true. Am I going too fast? But we've done this kind of stuff before. How are people doing? Right, so here, what happens if computational problem P is not even a computable problem? Suppose P is the halting problem, right? Now I say the sentence is still true, right? So the adversary gives us some really hard input for P, right? And now, right, the prover can work day and night to determine what the answer is for I, but the problem is P is uncomputable. So the prover can't find out what the answer is, the P of I. So he can't actually build the algorithm, right? He knows the problem is the halting problem. He knows the input is some crazy hard input, right? But he doesn't know what P of I is. Well, let's restate the game again. We're not saying here, when we say exist A, we're not saying that I can construct the algorithm. It's not saying I can construct it. It's just saying that the algorithm exists, right? So the prover doesn't have to actually construct it, right? Instead, the prover just proves that it exists. And he doesn't know what P of I is. He doesn't know what P of I is. It could be 1, 2, 3, 4. It could be yes. It could be no. He doesn't know it. But he knows that P of I is some integer or is some finite string or is true or false, right? He knows it's one of those. And he knows that for each such output, there's an algorithm that outputs that answer, right? So he knows that there exists an algorithm that gives the right answer, even if he can't find it, right? So what does this say? This says it's true, even for undecidable algorithms, right? It's not a good statement because there should be a different algorithm for each input. One, here's an algorithm that always says yes, here's an algorithm that always says no, and one of them gives you the right answer for this input. All right, what does this say? For every algorithm, there exists an input. This is what we did before, right? For every algorithm, there's in the input. But now we're saying that doesn't solve the problem.
Sorry, I think some people in the chat were a little bit confused about like when when the adversary goes. So it's always when there's a for all, the adversary goes, right? So in the case that the existential was first and the adversary, the for all quantifier was second, then the adversary would go second, right?
Good, good. So it's good to know that people out there are having a hard time, and so you're learning stuff. That's good. So let's review the game. She's absolutely right. Whenever you have a statement like this, you read it left to right. And whenever there's a for all, the adversary chooses it because the adversary is trying to give you a worst case object to make the thing false, right? The adversary is trying to give you an A for which it's false. And then knowing that we're reading left to right, so knowing the things that happened before, if it's an exists, then the prover is trying to prove it's true. So the prover gives you the object for which it's true, right? Now, that's the game. And what also changes is, are we trying to prove that it's true, or are we trying to prove it's false? If we're trying to prove it's true, then when the adversary goes, right, if we're trying to prove it true, then the prover is coming up with a strategy, right, in which the prover can win. And so when you're coming up with a strategy, we don't actually have the adversary around. So we say, let A be arbitrary, right? If we're trying to prove it true, we say, let A be arbitrary, then I tell you what I is, and I is a function of A.
That makes sense. Thank you.
Right?
Oh,
And if we're trying to prove it's false,
Sorry, we can't hear you.
Let me finish this sentence here. You can't hear me.
Yeah, for a bit, yeah.
Look at this.
It's fine for me.
That's because
Now I can hear you. Yeah, now it's fine.
All right. Sorry. That whole time we didn't have the mic on. So now the mic is on. And now we're not in the beginning at the right page anymore.
Yeah, I noticed that because the mic was not like how it was last time when you made it work correctly. Like
all right.
The audio.
So holler if that's. There's so many buttons. When I set up here, there's so many things to set up, and I didn't plug in my mic. All right. So what are we doing? We're doing this. All right. Let's.
Sorry, your voice is lagging again.
How much of this should I say again? How to solve that? Yeah. So here, I assume I have the right Wi-Fi. I mean, we could check my Wi-Fi. Come on. That's not even working. Why is that not working?
I guess it's fine now.
All right.
Yeah, now it's fine.
All right.
Apparently.
Yeah, we're connected to 2, so that's good. The two's right here in my room. Sometimes it connects to the one downstairs, and then it's not good. All right. So anyway, let's go back to what we're doing here. How does the game? Everybody get what the game is now? And what we're about to say, if we're trying to prove it's false. Yeah.
Oh, there
what?
You go. We can see now. We can see it now. Sorry.
All right. Again, the delay here. All right. So if we're trying to prove it's false, then the adversary is going to come up with we need it. If we're proving it's false, then the adversary has a strategy. So the adversary gives us an algorithm, and we have to, and then we say I is arbitrary. Anyway, this one here, are people getting this? This says on input out I algorithm fails to solve P. And so what does this say? This says there's some input on which algorithm A fails to solve P. And if that's true, if there's some input on which algorithm A fails to solve P, then what do we say? A doesn't solve P, right? If A doesn't solve P on every input, then it doesn't solve P. So this just says A doesn't solve P, right? Doesn't solve P for every input, so it doesn't solve P, right? And then here he's saying every algorithm, right? Every algorithm fails to solve P, right? P is not computable, right? That's what this says, right? Everybody buy that? Right? It says every algorithm fails to solve P. Why? Because P is not computable. In fact, if you take the negation of this, right? When you take the negation, for all turns into exists. The exist turns into for all, right? Not equal turns into equal, right? So that's the negation. And what does the negation say? It says it is computable. It says there is an algorithm that solves P for every input. Right? So it's the same game except we reverse the roles, right? For all input, we're trying to prove that this, right? The adversary provides the algorithm, right? It's a for all A, so the adversary provides the algorithm, and then the prover comes up with an input, and has to be false, right? Right, so here we're at some point I assume that P was computable, right? It's stating that P is not computable, no algorithm solves it. All right, everybody follow those examples?
Hey Jeff, yeah, I have a question.
This really is a delay.
So
it's funny. Look at this. Yeah.
Yeah, so I have a question. So if we have two universal quantifiers, then they're both adversaries, or which one is the first
right.
one is the,
and it doesn't matter which one goes first. For all Y, for all X, because the adversary is giving you both. So the adversary can plan and decide which to give first, right? If I'm playing a game with you and I have to provide you both X and Y, then I got to think ahead of time which X and which Y do I want to give you. And then it doesn't actually, once I decide which I'm going to decide some X and some Y, right? And then it doesn't matter which one I hand to you first.
Okay, so right. Order doesn't matter in terms of like if they're both adversaries.
Yeah, or both, right? If it's both for all or both exist, it doesn't matter which comes first.
Yeah, and if you have an exist first and a for all second, then you have the adversary second, because yeah, it's a for all. The for all is second.
Then it matters if you're alternating quantifiers. Yeah, we talk about how many alternations of quantifiers it is. We don't care how many quantifiers there are. It's how often do you alternate between a for all and exist, for all and exist.
You were lagging. You were lagging. You were lagging, by the way.
Yeah,
I didn't catch that.
Oh,
can you repeat? Sorry about that. I didn't catch that because you were lagging. Yeah.
All right. So, if I'm looking at how complex a sentence is, right, then what matters. Oops, I killed everything here. What matters is how many alternations there are between for all and exist, for all and exist, right? There could be many for alls together and many exists for together. That doesn't matter. How complex the thing is how often we alternate from for alls to exist. Right? Does that make sense?
Yeah, so in that case, yeah, so the adversary wouldn't be second if we had an exist quantifier first, and then we had a universal quantifier second.
Right. If it exists first, then the prover goes first.
Okay.
I don't understand. Like, so if you have where there's for all exists and there's another for all exists, but there isn't necessarily a for uh, for some like the other one. How would you go about it? Is it that you just say that the adversary won because there is no prover to prove it? So if you give me like an equation that does that, do you know what I mean?
You mean if it's just all exists?
Yeah, or if there's just all, yeah, if there's just all exists, yes.
Yeah, if it just all exists, then the game is really short. I construct things that I claim exist, and I prove that they have the right property. There's no adversary involved.
So you just straight up the prover just wins in that case.
Yeah, exactly. And if it's all for alls, then we let everything be arbitrary. If it's for all x, for all y, for all z, then I say let x, y, and z be arbitrary, and we prove that it's true for those.
Okay, thank you.
Sir.
All right. Yeah.
Can you explain the not computable example again, the last part? Because I think you're lagging. I think I misheard something.
All right. Where is it? Here it is. This is not computable, right? It says, how do we prove that P is not computable? What we do is the adversary gives me an arbitrary, the adversary is, I want to prove that it's not computable. So the adversary is trying to prove that it is computable, right? The adversary is trying to say it's false. So the adversary is trying to prove it is computable. So the adversary gives me some arbitrary algorithm, right? Let A be an arbitrary algorithm. And then my goal is to prove that this arbitrary algorithm doesn't solve the computational problem P, right? Now that's pretty hard to do, right? I've proven lower bounds, proving that things aren't computable. I have to come up with, I get to study your algorithm, even though it's hard to study it because it's an arbitrary algorithm, right? I study this arbitrary algorithm and I come up with some input and I prove that on that input, the algorithm doesn't in fact solve the problem. Right? Does that make sense?
Okay, then why is the last part say false?
Right? Because you give me an algorithm, I give you an input on which the algorithm does not solve the problem. It's not computable. Right? Here, if we take the do you know how to take the complement here? What's the negation of this is this, right? You buy that?
Yes.
Right, this one says, this is how you show it's computable. How do you prove to me, let's P be sorting. How do I prove that P is sorting? You give me I come up with an algorithm, say quicksort. Then you give me an input and I show you, oh look at quicksort gives the right answer for our sorting problem. That's how we show that that sorting is computable. How do I prove that the halting problem is not computable, right? The adversary gives me we play the reverse game, right? It's the reverse game. The adversary gives me an arbitrary algorithm, and I want to prove that this arbitrary algorithm does not solve the halting problem, right? How do I prove that this algorithm doesn't solve the halting problem? All I have to do is show you one input in which it fails, right? The algorithm that the adversary gave me might solve the halting problem on some inputs, right? But it doesn't solve it on all algorithms and on all inputs. Some algorithms it works for these inputs, some algorithms it works for those inputs, but for every algorithm there's some inputs on which it gives the right answer. So which it gives the wrong answer.
So the statement is true?
The statement is true if P is uncomputable. This
Okay.
statement is true if P is computable.
Yes, yes. So
Right?
why is the bottom one false? At the answer, say false. Why?
Oh,
The answer say false.
because when it's in white like this, it was cut out from the homework, from the test. And on the test at the top, it said that P was computable.
Oh, okay, okay. I
Right?
didn't know that. Okay.
Yeah, exactly.
Okay. What about if
Right?
the input?
It's stating that P is not computable.
What about if the input is for all? So for all input. So for all algorithm there, for all input and AI equal to PI.
All right, well, that's definitely false, right? Because
not all algorithms solve the problem, right?
yeah, not all algorithms solve the problem.
Okay, thank you.
Are people getting this? See, I don't know how fast to go because my sense is that hopefully everybody was getting this already, so I went kind of fast, but maybe you guys are struggling on this. The truth is, if you're struggling with this, then I really hope that you study this stuff and really get it, because this is the page that when you come to 2001, I want you to understand. It's funny, if it's a delay, it should be that, but maybe you don't get the picture and the sound at the same time.
You really lagged a bit just now.
Oh, it's really loud?
No lag. The lag was really.
Oh, the lag, yeah. Between the picture and the sound. Yeah.
So I was just wondering, so if you ask us this type of question during the test,
Yeah.
like we don't have to talk about like whoever goes first between the adversary or the prover. Like we just have to state if the statement is true or false and give the reason why. That's it.
Well, what I did on this test is I want
like you want step by step.
I want you to prove to me that you understand deeply what it means, right? So the one way, right? So here, right? The way I get you to build up meaning is to write this thing down at the bottom. But I found that students weren't able to do that, right? So I try hard to figure out what can I get people to say what it means down here. And so that's why I get them to build it up line by line, right?
So starting from the inside and
yeah, right.
Okay.
So maybe I'll get you to do that on a test so that you get a practice saying, "Hey, can I build up what it means?" Have you tried it? Do you find that building it up like this helps?
I think it makes more sense to do it this way than going from the outside and going toward the inside.
Right. So yeah, so when you're understanding it this way, and then when you're playing the game, you go the other way. The proof goes the other way, right? So I do find understanding goes one direction backwards and the proof goes forwards. And so
I'm sorry, can you repeat that?
I haven't made up the test.
You said the proof goes from the inside.
The proof goes forwards.
Forwards, okay.
No, the proof goes forwards, and the understanding seems to go backwards.
Okay.
Yeah, the proof goes forwards. The game goes forwards, right? So I have a whole list of, over the summer I made up some questions for the test, and I think that they might all be hard. But that's okay because your average is too high. But I should add in some questions like this that are a little easier, right? So a question like this, I just need everybody to be able to do. All right. Any more questions about this? Because we're about to go into something harder?
So for the last one, the one where A of I doesn't equal P of I,
Uh-huh.
so all you have to do is prove one scenario, the other one, yeah. So all you have to do is prove one situation where A of I does equal P of I, and then you've disproved it.
If we want to, if you
Sorry,
want to
repeat that.
disprove it, then you're playing this game, right? Then you're telling me giving me an algorithm, whether you're disproving this or proving this. What you're doing is you specify an algorithm such that for all inputs, it does solve the problem. That's how you prove this. That's how you disprove this. How do you prove this? Is given an arbitrary algorithm, you have to find an input in which it doesn't give the right answer.
But since there could be multiple inputs, what if there is an input that this works, where A of I doesn't equal P of I, but you find another input where A of I does equal P of I? I mean, so it could be any input.
Yeah, so does there exist an algorithm that gives you the right answer to the halting problem on all 100? Right?
Sorry,
Right,
could you repeat that, please?
Right, so here, let's say P is a really hard problem like the halting problem, right? So could God give you an algorithm that says if the input is 0, then here's the answer. If the input is 1, here's the answer. If the input's 2, here's the answer. If the input's 3, here's the answer, right? And it does it for so many lines, some finite number of lines of code, right? Could God give you such an algorithm?
I don't want to test the capabilities of God.
Yeah. All right, that's true. That's true. We don't. But the reason I talk about God is because I personally might not know the answer for the first million inputs of the halting problem, right? I might not know the answer, but I'm just saying that they exist, right?
Just saying that there is
there
some
are
algorithm.
that just happens. There's an algorithm that just happens to give the right answer for the first million inputs.
We just haven't defined it, or we just haven't
Yeah,
found it.
right. But if you give me an algorithm that happens to give the right answer in the first million inputs, then I'm going to give you the millionth and one input.
Okay. Do you have to prove that it exists by like solving it, or do you just assume that it exists?
No, in 2001 we proved this, and the proof is really elegant. And if we get to it, then I hope that we'll prove it in this class. The proof is really not very hard to prove that the halting problem is uncomputable. It takes two pages of screen like this. We can prove it. It's not very hard.
Okay. All right. Thank you.
Sorry, I still don't really get that. You said that there's an algorithm for all inputs, and now we're trying to find an algorithm for all inputs. Sorry, we're trying to find one algorithm for all inputs.
Yeah. The one in orange is saying that P is computable. It's saying that there exists an algorithm that gives you the right answer for every input. That's saying P is computable in orange. The white one says every algorithm fails on some input.
So if every algorithm fails on like some input, doesn't that mean there's also some input that the algorithm works on?
There might be. That's what I said. There could be an algorithm. Well, some algorithms might not work for any inputs. Some algorithms work with some inputs. Like there could be an algorithm that happens to give you the right answer on the first 1,000 inputs, right? Then there's another algorithm that happens to give you the right answer on the first 1,000,000 inputs. There might be an algorithm that gives you the right answer on the first 1,000,000,000 inputs. In fact, there is, right? The algorithm says, if input is 1, this is the answer. If input is 2, this is the answer. Input is 3, this is the answer. It does it for 1,000,000 lines, right? There's an algorithm that gives you the right answer for the first 1,000,000 inputs. But what this is saying is for every algorithm, there's some input on which it gives the wrong answer.
So that means since there's some input where it's wrong, it can't have all inputs. Like
Exactly.
Okay, so
Right?
so
If you're
sorry, I just wanted to be clear. Like what we're trying to do now is that we're using the negation to prove the actual thing.
just here, these are negations of each other. You show for every algorithm there is an input on which it doesn't give the right answer.
Sorry to cut you off again, but the lagging was really, really bad. I didn't even hear anything. Sorry.
All right. So if you want to prove this sentence is true, then you prove that for every algorithm there's an input. Sorry, if you want to prove it's true, if you want to prove that it's computable, if P is computable, how do you prove to me that sorting is computable? You give me an algorithm, say quicksort, and then I show that that algorithm works for every input, right? How do you prove that the halting problem is not computable? You give me an algorithm and I come up with an input in which it gives the wrong answer.